Right, we're going to continue exploring Chapter 8, which is titled Computer Reliability. And in particular, we're going to explore or cover sections 8.4 and 8.5. Section 8.4 is titled Notable Software System Failures. And in this section, we're going to shift our focus to complicated devices or systems controlled, at least in part, by computers. And we're going to talk about embedded systems. And an embedded system is a computer used as a component of a larger system. You can find microprocessor-based embedded systems in microwave ovens, thermostats, automobiles, traffic lights, and a host of other modern devices. So because computers need software to execute, every embedded system has a software component. And software is playing an ever larger role in system functionality, and there are several reasons why hardware controllers are being replaced by microprocessors controlled by software. For example, software controllers are faster. They can perform more sophisticated functions, taking more input data into account. They cost less, use less energy, and do not wear out. Unfortunately, while hardware controllers have a reputation for high reliability, the same cannot be said for software replacements. Most embedded systems are also real-time systems, which means they are computers that process data from sensors as events occur. The microprocessor that controls the airbags in a modern automobile, for example, is a real-time system because it must instantly react to readings from its sensors and deploy the airbags at the time of collision. So the microprocessor on a cell phone is another example of a real-time system that converts electrical signals into radio waves and vice versa. So this section contains 7 examples of computer system failures. The Patriot missile system used in the Gulf War, the Ariane 5 launch vehicle, AT&T's long-distance network, NASA's robot missions to Mars, the automated baggage system at Denver International Airport, the Tokyo Stock Exchange, and direct recording electronic voting machines. These are all examples of embedded real-time systems. And in every case, at least part of the failure was due to errors in the software component of the system. So studying these errors should provide important lessons for anyone involved in the development of an embedded system and the software in particular. So let's start with the Patriot missile. The Patriot missile system was originally designed by the U.S. Army to shoot down airplanes. In the 1991 Gulf War, the Army put the Patriot missile system to work defending against Scud missiles launched at Israel and Saudi Arabia. And the most significant failure of the Patriot missile system occurred during the night of February 25th, 1991, when a Scud missile fired from Iraq hit a U.S. Army barracks in Dhahran, Saudi Arabia, killing 28 soldiers. The Patriot missile battery defending the area never even fired at the incoming Scud missile. So let's say a little bit about why. The missile battery did detect the incoming Scud missile as it came over the horizon. However, in order to prevent the system from responding to false alarms, the computer was programmed to check multiple times for the presence of the missile. The computer predicted the flight path of the incoming missile, directed the radar to focus in on that area, and scanned a segment of the radar signal, which is called a range gate, for the target. In this case, the program scanned the wrong range gate, or the wrong segment of the radar signal. And so, since it did not detect the Scud, it did not fire the Patriot missile at all. So the question you want to know from mechanical point of view is or an engineering point of view is why did the program scan the wrong range gate? And the tracking system relied upon getting signals from the system's clock, and these values were stored in a floating point variable, so like a number with a decimal, and with values to the right of the decimal. But this floating point variable, it was stored in the floating point variable with insufficient precision, resulting in a small mathematical error called a truncation. So the longer the system ran, the more these truncation errors added up, and the Patriot missile system was designed to operate for only a few hours at a time. However, the system at Dhahran had been in continuous operation for 100 hours. So the accumulation of errors led to a difference between the actual time and the computed time of about 0.3433 seconds. But because missiles travel at high speeds, the 0.3433 second error led to a tracking error of 687 meters, about half a mile. That was enough of an error to prevent the missile battery from locating the Scud in the range gate area. And so that's pretty astounding, because floating point variables, to have that type of an error would be small, but given the truncation over the course of 100 hours and how fast missiles travel, that led to this half-mile error in the range gate. So something as simple as getting your floating point variables can save lives. Floating point variables correct can save lives. The Ariane 5 was a satellite launch vehicle designed by the French Space Agency and the European Space Agency. About 40 seconds into its maiden flight on June 4th of 1996, a software error caused the nozzles on the solid boosters in the main rocket engine to swivel to extreme positions. And as a result, the rocket veered sharply off course. When the links between the solid boosters and the core stage ruptured, the launch vehicle self-destructed. The rocket carried satellites worth $500 million, which were not insured. A board of inquiry traced the software error to a piece of code that converts a 64-bit floating point value into a 16-bit signed integer. The value to be converted exceeded the maximum value that could be stored in the integer variable, causing an exception to be raised. And unfortunately, there was no exception handling mechanism for this particular exception, so the onboard computers crashed. So the faulty piece of code had been part of the software for the Ariane 4. The 64-bit floating point value represented the horizontal bias of the launch vehicle, which is related to its horizontal velocity. And when the software module was designed, engineers determined that it would be impossible for the horizontal bias to be so large that it could not be stored in a 16-bit signed integer. So there was no need for an error handler because an error could not occur. This code was then moved as is into the software for the Ariane 5. But that proved to be an extremely costly mistake because the Ariane 5 was faster than the Ariane 4. So the original assumptions made by the designers of the software no longer held true. All right, and then AT&T's long distance network serves as another example of getting your software components correct. So here it is. On the afternoon of January 15th, 1990, AT&T's long distance network suffered a significant disruption of service. What happened was that about half of the computerized telephone routing switches crashed, and the remainder of the switches could not handle all the traffic. So as a result of this failure, about 70 million long-distance telephone calls could not be put through, and about 60,000 people lost all telephone service. AT&T lost tens of millions of dollars in revenue, and it also lost some of its credibility as a reliable provider of long-distance service. An investigation by AT&T engineers revealed that the network crash was brought about by a single faulty line of code in an error recovery procedure. In particular, the system was designed so that if a server discovered it was in an error state, it would reboot itself, which was a crude but effective way of wiping the slate clean. But after a switch rebooted itself, it would send an OK message to the other switches, letting them know it was back online. And the software bug manifested itself when a very busy switch received an OK message. Because under certain circumstances, handling the OK message would cause the busy switch to enter an error state and reboot. All right, the robot missions to Mars serves as another example. NASA designed the $125 million Mars Climate Orbiter to facilitate communications between Earth and automated probes on the surface of Mars, including the Mars Polar Lander. Ironically, the spacecraft was lost because of a miscommunication between two support teams on Earth. The Lockheed Martin Flight Operations team in Colorado designed its software to use English units, so its program output thrust in terms of foot-pounds. The navigation team at the Jet Propulsion Laboratory in California, however, designed its software to use metric units, so its program expected thrust to be input in terms of newtons. 1 foot-pound equals 4.45 newtons. So on September 23rd, 1999, the Mars Climate Orbiter neared the red planet, or Mars, and when it was time for the spacecraft to fire its engine to enter orbit, the Colorado team supplied thrust information to the California team, which related to the spacecraft. But because of the unit's mismatch, the navigation team specified 4.45 times too much thrust, and the spacecraft flew too close to the surface of Mars and burned up in its atmosphere. A few months later, NASA's Martian program suffered a second catastrophe. The Mars Polar Lander, produced at a cost of $165 million, was supposed to land on the south pole of Mars and provide data that would help scientists understand how the Martian climate has changed over time. On December 3rd, 1999, NASA lost contact with the Mars Polar Lander, and NASA engineers suspect that the system software got a false signal from the landing gear and shut down the engines 100 feet above the planet's surface. Okay, the Denver International Airport is another example of what happens when you don't get your software components designed correctly. And so as airline passenger traffic strained the capacity of Stapleton International Airport, the city and county of Denver, Colorado, planned the construction of a much larger airport. And the airport authorities signed a $193 million contract with BAE Automated Systems to design and build the automated baggage handling system, which consisted of thousands of baggage carts traveling roller coaster style on 21 miles of metal tracks. To monitor the movement of the bags, the system used 56 barcode scanners and 5,000 electric eyes. There were problems from the outset of the project, however. For example, the airport design was already completed before the baggage handling system was chosen, so as a result, the underground tunnels were small and had sharp turns, which made it difficult to shoehorn in an automated baggage system. And given its ambitious goals, the project timeline was too short. However, the most important problem with the automated baggage handler was that the complexity of the system exceeded the ability of the development team to understand it. Eventually, the mayor of Denver announced the city would spend $50 million to build a conventional luggage handling system using tugs and carts. And this conventional system actually ended up costing $71 million. So the failure of the BAE to deliver a working system on time resulted in a 16-month delay in the opening of this new airport in Denver, and ended up costing Denver $1 million a day in interest on bonds and operating costs. As a result, the DIA began charging all the airlines a flight fee of about $20 per passenger, which was the highest airport fee in the nation. And airlines went ahead and passed along this cost to consumers by raising ticket prices of flights going through Denver. So while the story of the Denver International Airport, or DIA, is noteworthy because of the large amount of money involved, it is not unusual for software projects to take longer than expected and to cost more than anticipated. In fact, most software projects are not completed on time and on budget. And so we'll explore that issue in greater detail in section 8.9. All right, the Tokyo Stock Exchange is another interesting example involving software component errors. So on December 8th of 2005, that marked the first day that shares of JCOM, which was a recruiting company, were made available to the public on the Tokyo Stock Exchange. That morning, an employee of Mizuho Securities received a call from a customer who said he wished to sell one share of JCOM stock at a price of 610,000 yen. At 9:27 a.m., the Mizuho Securities employee mistakenly entered an order to sell 610,000 shares of JCOM at 1 yen per share. And when the computer displayed a beyond price limit warning, the employee overrode the warning by hitting the enter key twice, sending the order to the Tokyo Stock Exchange. At 9:28 a.m., the sell order appeared on the Tokyo Stock Exchange's display board, and spotting the mistake, Mizuho Securities attempted to cancel the sell order several times between 9:29 and 9:35 a.m., so about a 6-minute window, but these attempts failed because of a software bug in the Tokyo Stock Exchange trading program. So beginning at 9:35 a.m., Mizuho started to buy back shares of JCOM, but it was only able to purchase about 500,000 shares. More than 96,000 shares had already been purchased by other parties, so it was impossible for Mizuho to provide shares to these buyers because JCOM only had 14,500 publicly traded shares. So under the terms of a special arrangement brokered by the stock exchange, Mizuho settled these accounts by paying 912,000 yen per share to the buyers. So in all, Mizuho Securities lost 40 billion yen, or about 225 million US dollars, buying back shares. Okay, direct recording electronic voting machines are another interesting example we should say something about. So nearly 2 million ballots were not counted in the 2000 US presidential election because they registered either no choice or multiple choices. And the incredibly close election in Florida was marred by voting machine controversies that we already discussed in Chapter 7, Section 7.5. So to avoid a repeat of these problems, Congress passed and President Bush signed the Help America Vote Act of 2002, or the HAVA Act, or just HAVA. And HAVA provided money to states to replace punch card voting systems and improve standards for administering elections. Many states used HAVA funds to purchase direct recording electronic, or DRE, voting machines. DRE voting machines allow voters to indicate each of their choices by touching the screen or pressing a button. After all selections have been made, a summary screen displays the voter's choices. At this point, the voter may either cast a ballot or back up to make changes. Brazil and India have run national elections using DRE voting machines exclusively. So by the time of the November 2006 general election, about 1/3 of US voters cast their ballots on the DRE system. So proponents of DRE voting machines pointed out the speed and accuracy of machine counting, and they said the systems were more tamper resistant than paper ballots, which can be marked by election workers. Moreover, when the ballots are electronic, it is impossible for precincts to run out of ballots if turnout is higher than expected. And in addition, touchscreen voting machines can be programmed to help voters avoid the previously mentioned errors of not choosing a candidate or selecting too many candidates. But there are issues with DRE voting machines as well. So some computer experts spoke out against the conversion to touchscreen voting machines, arguing that they are not necessarily any better than the systems they are replacing. And in particular, experts expressed concerns about programming errors and the lack of a paper audit trail or a record of the original ballots cast. And quite a few voting irregularities were linked to DRE voting machines since 2002. And moreover, some computer experts expressed concerns about the vulnerability of electronic voting machines to tampering. In particular, without access to the source code to touchscreen systems, there is no way to test how secure they are. The manufacturers of these systems refused to make the software public, saying the source code is valuable intellectual property or a trade secret. But supporters of touchscreen voting machines said criticisms of DRE voting machines were overblown. A report by the Pacific Research Institute maintained that DRE voting systems are more secure than traditional paper ballots, which can be tampered with by election officials. Nevertheless, most states had second thoughts about DRE voting machines, and in May of 2007, Florida's legislature voted to replace DRE voting machines with optical scan ballots. Voters select candidates by filling in bubbles next to their names, and optical scanning machines count the marked ballots. And this approach has the benefit of leaving a paper audit trail that makes possible manual recounts in disputed elections. By the time of the general election in November of 2004, 70% of Americans were back to casting old-fashioned paper ballots. Pamela Smith, president of Verified Voting, said paper, even though it sounds kind of old school, actually has properties that serve the elections very well. All right, section 8.5 is titled Theric 25, and in 1895, the X-ray was discovered by the German physicist Wilhelm Röntgen, and after 1895, physicians began using radiation to treat cancer. Linear accelerators create high-energy electron beams to treat shallow tumors, and X-ray beams to reach deeper tumors. The Theric 25 linear accelerator was notoriously unreliable, however. It was not unusual for the system to malfunction 40 times a day, and we're going to devote an entire section to telling the story of the Theric 25 because it is a striking example of the harm that can be caused when the safety of a system relies solely upon the quality of its embedded software. So the genesis of the Theric 25 has to do with a company called Atomic Energy of Canada Limited, or AECL, and the French corporation CGR. They cooperated in the 1970s to build two linear accelerators, the Theric 6 and the Theric 20. After producing the Theric 20, the AECL and the CGR went their separate ways. The AECL moved ahead with the development and deployment of a next generation linear accelerator called the Theric 25. So like the Theric 6 and the Theric 20, the Theric 25 made use of a PDP-11. But unlike its predecessor machines, AECL designed the PDP-11 to be an integral part of the device. The linear accelerator was incapable of operating without the computer, actually. So this design decision enabled AECL to reduce costs by replacing some of the hardware safety features of the Theric 20 with software safety features in the Theric 25. AECL also decided to reuse some of the Theric 6 and Theric 20 software in the Theric 25. Well, one obvious reason they made this decision was that code reuse saves time and money, and theoretically, tried and true software is more reliable than newly written code, but as we shall see, that assumption was invalid in this case. So AECL shipped its first Theric 25 in 1983, and in all it delivered 11 systems in Canada and the United States. The Theric 25 was a large machine that was placed in its own room, and shielding in the walls, ceiling, and the floor of the room prevented outsiders from being exposed to radiation. A television camera, microphone, and speaker in the room allowed the technician in an adjoining room to view and communicate with the patient undergoing treatment. In a 20-month period between June of 1985 and January of 1987, the Theric 25 administered massive overdoses to 6 patients, causing the deaths of 3 of them. So what were the software errors inherent to the embedded system of the Theric 25? Well, in the course of investigating the accidents, AECL discovered a variety of hardware and software problems with the Theric 25. 2 of the software errors are examples of race conditions. So in a race condition, 2 or more concurrent tasks share a variable, and the order in which they read or write the value of the variable can affect the behavior of the program. Race conditions are extremely difficult to identify and fix because usually the 2 tasks do not interfere with each other and nothing goes wrong. It's only in rare conditions that the tasks actually interfere with each other as they manipulate the variable, causing the error to occur. And we'll describe both of these errors to give, the book goes into great detail about both of these errors, and I'll leave you to read more about that. But the accidents at the ETCC occurred because of a race condition associated with the command screen, and one task was responsible for handling keyboard input and making changes to the command screen, while a second task was responsible for monitoring the command screen for changes and moving the magnets into position. All right, so to do a post-mortem, which is sort of like a lessons learned about what went wrong after a project or endeavor is attempted or completed, and even as a failure, that's what the AECL did. They considered the mistakes that were made in the design, development, and support of the Theric 25. So when the accidents were reported, the AECL focused on identifying and fixing particular software bugs. That was their first mistake because such an approach was too narrow because the entire system was broken, not just the software. The real problem was that the system was not designed to be fail-safe. Good engineering practice dictates that a system should be designed so that no single point of failure leads to a catastrophe. And by relying completely upon software for protection against overdoses, the Theric 25 designers ignored this fundamental engineering principle. And another flaw in the design of the Theric 25 was its lack of software or hardware devices to detect and report overdoses and shut down the accelerator immediately. Instead, the Theric 25 designers left it up to the patients to report when they had received overdoses. There are also particular software lessons we can learn from the case of the Theric 25. First, it is very difficult to find software errors in programs where multiple tasks execute at the same time and interact through shared variables. Second, the software design needs to be as simple as possible, and design decisions must be documented to aid in the maintenance of the system. Third, the code must be reasonably documented at the time it is written. Fourth, reusing code does not always increase the quality of the final product. Obviously, the AECL assumed that by reusing code from the Theric 6 and Theric 20, the software would be more reliable. After all, it's not totally unreasonable because the code had been part of systems used by customers for years with no problems. So the problem, of course, is that assumption turned out to be wrong. The earlier codes did contain errors, but these errors remained undetected because earlier machines had hardware interlocks that prevented the computer's erroneous commands from harming patients. And the tragedy was compounded because AECL did not communicate fully with its customers. For example, AECL told the physicists in Washington and Texas that an overdose was impossible, even though AECL had already been sued by the patient in Georgia. So we can look at a question involving how much moral responsibility or blame should be placed on the Theric 25 team. So should the developers and managers at AECL be held morally responsible for the deaths resulting from the use of the Theric 25 that they produced? Well, philosophically, we can do an analysis to figure out what it means for a moral agent to be responsible for a harmful event. It seems like there are two necessary conditions that must obtain or hold in order for a moral agent to be held responsible for a harmful event. The first condition we can call the causal condition, and this states that the actions or inactions of the agent must have caused the harm. That's the causal condition. And then the second condition that must obtain is the mental condition, which says that the actions or inactions must have been intended or willed by the agent. So in this case, the causal condition is easy to establish. The deaths resulted both from the action of AECL employees creating the therapy machine that administered the overdose and the inaction of the AECL employees who failed to withdraw the machine from service or even inform other users of the machine that there had been overdoses. All right, well, what about the mental condition? Well, surely the engineers at AECL did not intend or try to create a machine that would administer lethal overdoses of radiation. However, philosophers also extend the mental condition to include unintended harm if the moral agent's actions were the result of carelessness, recklessness, or negligence. So the design team took a number of actions that fall into these three categories. It constructed a system without hardware interlocks to prevent overdoses or to keep the beam from being activated when the turntable was not in a correct position. And the machine had no software or hardware devices to detect an accidental overdose. And management allowed software to be developed without adequate documentation. And it presumed the correctness of reused code and failed to test it thoroughly. So for these reasons, the mental condition would seem to hold or obtain as well, and we can conclude that the Theric 25 team at AECL is morally responsible for the deaths caused by the Theric 25 radiation therapy machine. So 3 decades after the Theric 25 accidents, computer errors related to radiation machines continued to maim and kill patients. In late 2006, Scott Jerome Parks received 3 overdoses from a linear accelerator at a New York City hospital that led to his death a few weeks later, and he was only 43 years old. About the same time, at another New York hospital, 32-year-old breast cancer patient Alexandra Jean-Charles received 27 straight days of radiation overdoses that led to her death. An investigation of radiation overdoses by the New York Times concluded that a variety of errors, including faulty software, were leading to crippling or fatal accidents.